still don't know what's going on.
Okay. What? It's a pencil going through a lens. How is that horrible?
That just looks bad. I just don't.
Oh, this is the easy one.
Sean, you're in optics. Chill out. Don't think about
Clearly, this is the easy one. This is why I'm starting with this.
convex lens.
Okay? All right. So, a couple of things that I'm going to do. One is I'm going to pass this around. Okay? So, depending upon which side you hold it, because it is a mirror, the cool thing about that is that it can actually, depending upon your perspective, either be a convex or a concave mirror. Okay? So I'm going to pass this around. Here's what I want. I want you to do three things. Okay? I want you to hold it where it is a concave mirror, like the curved side is closest to you. Okay? Now, so what I want you to do is hold it really close, like you'll have to get probably within like about 10 centimeters. And then you can look and see horrible things on your skin because it magnifies it, okay? And observe if it is upright or if it is inverted. Then I want you to slowly move that away, and then eventually you'll be able to see yourself again, but you're going to look completely different, okay? So I want you to hold it up close, get it where you can see it, then move it away. It's going to get blurry. Then see what happens when you get probably about a foot away from that, okay? The next thing I want you to do is flip it over, so then you're looking at the convex side of it, okay, where that light is bouncing off and doing this. Then I want you to do the same thing. I want you to hold it up close, and then move it away, and then see if that image flips like the other one did, okay? So hold it like this, concave. Up close, maybe give that a look. Further away, and you kind of have to adjust that, but then see what happens. And then like this, up close, further away, see what happens with that, okay? So,
Question.
what?
How do one-way mirrors work?
How what?
One-way mirrors.
Basically, the one coating is a reflective surface, obviously, that one. And the other side of it is, I can't remember the actual chemical nature, but basically, it allows those photons to pass through, but only in one direction. So, and I can't remember exactly what that is. Okay, so here's the next thing that we've got. And this works well with M&Ms, which sounds good. So now, don't be like nerdy little elementary kids here. Oh, I've seen that before. I know how that works. Shut it. If you've seen it, don't go, I've seen that before. Why don't you tell me? So, what I've got is a mirror like this, concave, convex. Very much concave, okay? And this is one of those deals, if you hold it up close, you get like this really that's big. And then if you hold it up far away, then if you can see that, notice that I am upside down, okay? So the cool thing about this is that light comes in, it hits the bottom, it bounces off, and then it reconfigures it. But if I put some M&Ms in the bottom, and if you get down and look, it appears that the M&Ms are hovering up above. So you have to get really close to actually see that. But if you get just right,
That's whack.
then it will actually look like the M&Ms are right here on top of the mirror. So you can't see this from a distance. You need to get closer. You can actually see that.
No, not really. I didn't think so.
No, 'cause then
It's kind of hard with the stand in the way.
Would you like me to help?
No, I just have to take out the stand.
No, I have a better idea. Just never mind.
It's interesting.
Have you tried to do it with the camera? Yes.
Kind of.
I got up.
You can see it.
Wait, tap the button back.
Do not eat them, Cohen. What? Those are not Pop-Tarts.
Wait a second. Those aren't right there?
No, they're not.
I hunger.
Oh, there they are.
It just looks flat.
No, is that?
I was trying to protect you, but it's Cohen's fault. Dude.
It's all good until Cohen's,
Gets involved.
It's just so
you
bad.
can't have nice things.
He's the one that knocked it over.
I
I was hungry.
Hologram. Not hologram. Dude. It's such a stronger hologram.
Oh yeah.
This is just, yeah, I think.
It just looks flat.
I have an idea, and it's like.
It just looks
What breaks my brain more is that it feels like there's like a something there that you're sitting on, but it's not. It looks like plastic.
Yeah, how far below the top?
If anything, it's always Charles' fault.
Okay.
See these M&Ms. Let's see how that
It's not,
Just tell me what, yeah, it's not just finished.
No, I bought too much. Okay.
it's cool.
This is gonna be the record.
It's like we're in the
All right, Cohen, you've seen it, go. Charles, you've seen it, go.
I'm done with my homework.
Go eat it.
Okay. All right, so here's what we're gonna do. So take yonder sheet that I gave you all yesterday. So we're gonna start with one that's relatively simple and one of the classic ones, okay? So as we go through this, there's going to be certain patterns that you're going to see. And then there's also going to be patterns that will break down, okay? So, and again, if there's ever a unit that is very specific in terms of terminology, this is it. If you ever are into, like, if you're into flashcards for vocabulary or diagrams, this would be the unit to embrace that idea. Because, like, if I tell you in a problem, hey, it's a convex lens, and you don't know what a convex lens looks like, you can't even do the problem, okay? Or if I tell you that, hey, it's a concave mirror, which works completely different than a convex mirror, and if you don't know what those look like, again, you can't do anything. So what this has, and this is like the classic, hey, this is how this field works. So over here on this one, I've got a converging lens. Okay, so let's just start with the terminology. So the converging lens, AKA known as what type of lens? Instead of converging, what else could I say? Convex. Convex. Okay, so we got a convex lens. Now, here's one of the first things that you have to decide is that what are you going to do with the sign of the focal length? Because if you don't have your focal length sign right, everything else is going to be wrong. So that's one of the most important things that you need to decide right from the get-go. Is your focal length going to be positive, or is your focal length going to be negative?
Is it going to be immediately obvious?
Somewhat. How about that? But once you see it, then it becomes obvious. Maybe not at the beginning, but it will be. So, here's the deal. So, when you draw these ray diagrams, typically you need a minimum of 3, because what the first 2 will do is kind of get you where you need to be, and the third one basically confirms, hey, this is what we've got. So as you draw array diagrams, and you're going to draw a lot of them, you need a good ruler and a sharp pencil, okay? And if that's, oh man, I hate drawing technical, you're screwed, okay? You are going to hate optics, right?
I already do. We've made it like.
I'm sorry, tough. So, just saying. So you need a good ruler and a sharp pencil, okay? Really dull, like pencils that draw big lines, horrible, okay? You need a good, sharp pencil and an even sharper mind. Just saying. Now, so what we're going to do is kind of work through this initially. And like I said, you're going to begin to see some patterns. So when you have a lens and mirror, it doesn't make any difference. There's 3 dimensions that you need. You need the focal length, and the focal length is determined by the lens or the mirror. Okay? You can't adjust that. The only time that really changes is if you put it like underwater where your indexes of refraction change, but unless that's a real specific situation. So unless you do something like that, the focal length is just a fixed value. Then you have the distance to the object, okay? That's how far away is that object from the lens or the mirror, and then you're going to have your image distance, which is going to be how far that is either from the mirror or the lens. So those are going to be your big 3, focal, object, image. Now, the good news is one of them doesn't require any thought. Object distance will always be positive, okay? You don't have to guess, ooh, do I make object positive or make object distance is always positive, okay? There's no guesswork to it. Object distance is always positive, okay? Cool with that, you don't have to guess. And again, this is what we talked about yesterday. If the light is brought together, whether it's a mirror or a lens, doesn't make any difference, the focal length is positive. Positive people bring people together, okay? If it's a lens and it diverges that light, or if it's a mirror and it diverges that light, that focal length is negative. And the beauty of it is there's no exceptions to that rule. It isn't like, well, sometimes the focal length is positive if it brings it together, but negative if it still brings it together, but it's on the other side of the lens. No, okay? Okay, there's no exceptions. There isn't this caveat that says, well, focal length is positive, but only if it's on one side of the mirror. No, okay? It's always positive or it's always negative. There's no exceptions to the rule once you begin to see what's happening. Now, based upon this diagram that's behind me, you have a convex lens or a converging lens. So therefore, the focal length is going to be positive or negative? Positive. Now, you've got a certain object distance. That object distance is going to be always positive. Now, this is going to be your image distance. So, a couple of things about this. Number 1, notice that the image is inverted. Okay? So, that's one of the things. Your images can be one of 2 things. It's either upright or it's inverted. Okay? And you'll see how you can figure that out later on. Then it's either real or it's virtual. So basically, if you can project it, this is a simple definition, if you can project it onto a screen, that's a real image. If you can't, then it's a virtual image, okay? Now, don't think, oh, virtual image, oh, that's the image of a lesser optical god. Okay? No, okay? Just because you can't project it on a screen doesn't mean it's like, It isn't like the other images look down on it and go, you can't be projected on a screen, you suck, okay? That,
What's like an image you couldn't project?
I'll show you in just a second.
Alright.
Yay.
Or if you take that convex mirror, and when you looked at it,
Oh, because like the dimensions don't line up right?
yeah, because that light's being scattered. So since that light's being scattered, I can't project it onto the screen. Okay, so here's what we've got. So on this, notice I can change this around. Now let's talk about these yellow dots. The yellow dots are the focal lengths. So notice here, you've got a focal length on both sides, right? You always have a focal length on one side, you always have a focal length on the other. With this one, and typically you draw at least 3 ray diagrams. Now, in reality, there are infinite number of these. So this is just drawing the tip of the pencil, goes through, hits the top of the lens, goes through the focal point. One goes straight through, one goes through the focal length over here, hits the lens, and then it goes parallel, okay? And there's no easy way for me to teach it. It just kind of comes with experience, okay? How do you draw them? What are they, and I'll give you some tips along the way, okay, especially with mirrors, there's some tips to make things simple. But if you can, it just kind of comes with experience, like, okay, hey, what are these ray diagrams going to do? Okay, so, got the visual of what this is going to look like. So what we're going to do is go through and we're going to work this one right here on this first one. So, what I've already given you the diagram. You know what it looks like. So what you've got is that you've got this lens, and I always use an arrow. You can use a carrot, you can use a paintbrush, a candle if you're old school, okay? But you need something that has a discernible top and bottom to it, okay? That's why I said yesterday, just don't draw a stick, okay? Because then you don't know if it gets inverted or if it's upright, because you don't know what's happening. So, we've got this arrow. Now, when you guys do these, okay, some of these I am going to specifically tell you, you draw these to scale, okay? Some will just say make a sketch. If I just say, hey, make a sketch, don't worry about it, doesn't have to be anything, you know, like drawn out with a ruler. But if I tell you, draw an actual ray diagram to scale, you're going to say, hey, like on this one, focal length is like 40 centimeters. Well, it really doesn't practically make sense to have a focal length of 40 centimeters. That's a pretty big distance, okay? So what you could do is like, hey, I'm going to let on my scale, I'm going to let 1 centimeter equal 5 centimeters. Oh, okay, hey, I can do that. 40 centimeters, I divide it by 5, I get 8 centimeters. That's something that I can fit on my paper. So just because it says, hey, the focal length is 40 centimeters, or 20 centimeters, whatever that is, that doesn't mean that you actually have to draw it to that size. You can pick a scale so that you don't actually have to draw them to that full size. Okay, now, here's the deal. So on this one, you've got a focal length of 20 centimeters, okay? So how most diagrams or problems play out, okay? This is typically how they play out. Typically what you're trying to find is the image distance, okay? 90% of the time, that's what you're after. So if you look on what you have on your equation sheet, you have 1 over so plus 1 over psi equals 1 over the focal length, okay? So basically, the optical god spoke and said, woo, here's your equation, okay? Works, but it's inverse, okay? It's the inverse. This is going to be important. These are going to be inverses. So, if you look at this diagram, so one of the ones, the simple to do on a diagram like this is draw a line parallel with it. So imagine that there's a photon that's being bounced off the top of that arrow, and it's going to travel parallel with it. Now, in reality, you have infinite number of photons. We're just going to pick one of them. But we're going to treat it like it's a ray. So the whole point of a lens is that it changes the angle. Okay, when it hits that, it bends it. So what's going to happen is this one's going to go through, and it's going to try and go through the focal length on the other side of this. Okay? Now, that by itself is not going to tell me where the image is. So, and here's the reason why. At this point, I have 2 options. It could be up here, and if it's up here, then the image would actually be upright, because that represents the tip of the arrow. So if it's to the left of that focal point, it's going to be upright. If it's on the other side of that focal point, then it's going to get flipped over, and then it's going to be inverted. So here are my two options, just based upon that one ray. I have two places that this can be. It's either on the left side of that focal point and upright, or it's on the other side of that focal point and it's inverted. That's why you can't base a ray diagram off of one ray. You have too many unknowns. You don't know what you've got. So let me get rid of this. So here's going to be the next thing. Now, the second easiest one to draw is the one that goes right through the middle. So this one's going to hit here, and it's going to start up here, and it's going to go right through that middle. Okay? Now, at this point, I've narrowed it down, because this goes right through the middle of that lens, and where these cross on the other side, that's telling me, hey, now I got a pretty good idea of where that image is going to be. And again, notice that the image is not at the focal point. Sometimes it is, but that's pretty rare. So get out of your minds right now that the focal point is where you see the image. Bad. No, stop. It's bad. Get rid of that thought right now. All the focal point tells you is where the rays are going to try and go through. Now, to solidify this, we're going to draw a third one. So we're going to go through this near focal point, and then it's going to hit that lens, and then it's going to go parallel, roughly. Well, I free-handed this whole thing, so we're okay. So what this one does is that it verifies and says, okay, this seals the deal. If those three meet at that same point, you know you got it right. If they don't, whoa, something's wrong. Now, this is why you draw three. Like I said, in reality, every one of these points is emitting a light, okay? The only thing we're going to do is pick what we call the three principal ray diagrams. So that's what the diagram is going to look like. Now, let's talk the math side of it. So if you look at the numbers that you've been given, so on this one, let me kind of redraw this. You've got this. Here's your focal length. Here's your focal length. Everywhere a focal length. Here's this. And your object distance is 40 centimeters. Your focal length is 20 centimeters. And what you're searching for is the image distance. Okay? So, here's your bread and butter. Okay? Your bread and butter is 1 over psi plus 1 over so equals 1 over f. Okay? It's your bread and butter. So in this situation, I want to solve for the image distance. I gave you the object distance, that's 40. I gave you the focal length, that's 20. Okay? So, I need to get the image distance by itself. So that's going to be 1 over psi is going to equal 1 over f minus 1 over so. This is not focal length minus object. It's the inverses of these. So in this situation, I'm going to take 1 over 20. Now, why did I keep that focal length positive? Because it's converging the light. Okay? If the light had been diverged, I would have made that a negative 20. Okay? So don't look at this and go, oh, that's 20 because it's a positive number and it's always going to be a positive number. No, that's positive because of the fact that the light is being brought together. Okay? Now, my object distance is 1/40. And again, you don't have to guess on the object distance. You don't have to guess. The object distance is always a positive number. So, to get the image distance, and this is where calculators come in handy. So you're going to take 1/20 minus 1/40 and then do what?
Take the inverse of that.
And then you take the inverse of that to get the image distance. Okay? Good with that. So somebody do the math. Take 1/20 minus 1/40 and then take the inverse of that.
40 centimeters.
You get 40 centimeters. Now, I don't want you to look at this and go, oh, image distance is always the same as your object distance. No, it randomly happened to work out that way, okay? Don't think, oh, these are easy. Those numbers are just always going to be the same. No, stop, okay? It randomly worked out that way, but that is not always going to be true. So, if you look at this, basically the only variable that I can manipulate on this is where do I put the object distance? Do I increase it? Do I decrease it? What do I got? Now, here's what's important. And this will play out large as you look at more and more of these. Notice on this one, the object is outside the focal length, okay? Sometimes that's important, sometimes it isn't. This particular one, as comparison to some other ones, you'll see that this is kind of important because it's going to tell you how the ray diagrams are going to go. Now, so we've got this. So my object distance, so if you want to play along, okay? So if you look at this in terms of magnification, magnification is high over ho, okay? Image height over object height. Now, there's a second way that you can calculate magnification. I can't remember if you, hold on. Yeah, psi over so. Now, your book has these as absolute, or excuse me, your equation sheet has these as absolute values. It gets a little bit wonky, I don't know why. But if you look at this in terms of high over ho, which is going to be the image height over the object height. So a lot of times, because these are going to be the same, in this situation, what I want to look at is psi over so, because that's what I know. So if I look at this in terms of psi over so, I've got 40 over 40. Now, here's what's important. Notice on this that as it is written, this is going to be a positive value. This is what I don't like about how the AP handles this, because most of the time there's actually a negative sign that lurks out there. The AP puts this as an absolute value. Your book actually has a negative sign in front of that. I would prefer that you keep track of that negative sign, and you'll see why, because that gives you some information. So in this situation, if I take negative 40 over positive 40, notice I get a magnification of -1. So here's the first trend that I want you to see. Notice that you have a negative magnification. What do you notice about your image?
It has a negative height.
Well, is it upright or inverted? It's inverted. So what you'll see, and this will play out large later on, if you have an inverted image, whether it's a mirror or a lens, if you have an inverted image, you're going to have a negative magnification. But you won't get that out of how it's written on your AP sheet, because they have it in terms of absolute value. In reality, it makes it simpler if you slip in a little negative sign and go, hey, what's the little negative sign between friends? What's that look like? Okay, so here's what we've got. the other thing that you can do in terms of figuring out a theoretical image height is that I've told you in the problem that the object height is 2 centimeters, which is going to be about like yay. So I gave you the fact that that's going to be 2 centimeters. Now, if I'm trying to find my image height, that's going to be my object height times my magnification. Now, these, it really doesn't make any sense to invoke the negative sign. Mainly because of the fact that negative signs in terms of the 7 dwarfs and hi-ho, that really doesn't make much difference. But it makes a much more difference when you get into the object and the image distances. So the magnification, hey, in terms of hi and ho, keep that as the absolute value. But the psi and the so, worry about the negative sign. So, in this situation, my magnification is 1. I take that times 2 centimeters, I get 2 centimeters. So what that means, very simply, is that you're going to project an image that's the exact same size as what you started with. It's just going to be flipped over on the other side. Okay? That's all that means. So, now, so if you look on this, is it upright? No, it's inverted. It's a real image because I can project that onto a screen. Now, here's another thing that you can look at, okay? In this situation, notice that when I found my image height, or my image distance, notice that that was a positive value. This will make sense as you do more of these. But if you have a positive image distance, what that will tell you is that the image is in the direction that the light is traveling. So if you look at this, the light's going this way and it's continuing on. So if that light is in that same direction, and that's just following the path of that light, nothing is getting bounced back, nothing's being flipped over, okay? So if it's in the same direction that the light is going, then that's going to be a positive value, okay? So, got that one. All right. Now, let's see one that's a little bit tougher to see. Don't even bother to take the camera, you won't be able to see anything. So, let's go to the back of the room.